Let's learn about the stiffness method for the first week. So every physical phenomena, whether it's a bar in tension or heat transfer through a body, can be modeled as a spring system. And the stiffness method that we will be covering this week and for the rest of the class is one of the methods used in FEM or finite element method to solve these physical problems. But before we jump into the stiffness method, let's understand or refresh our memories of what a spring is. A spring has a stiffness K, and the relationship between the force and displacement is given by this equation. So if you have a spring like that, sitting at a equilibrium position, and a force is applied to it, and because of this force F, we have a displacement of delta x or x along its length, we will have this equation. Force, which could be in newtons, is related to displacement or deformation, which could be in meters, by a stiffness of the spring as in the unit of newtons per meter. So if you have a bar like this with Young's modulus of E and Poisson ratio of nu at the length of L and cross-section area of A, and a force like F is applied to its top surface or one of its ends, which is in putting the bar in tension, and the bar is also fixed at one end, we know from solid mechanics that the relationship between the stress and force is given by this equation. Stress is equal to force over cross-section area. And we have strain, epsilon is equal to delta L over L. Delta L is deformation because of this force, and L is the initial length. Now if we apply the Hooke's law, we know that stress is equal to strain multiplied by Young's modulus. So sigma equals E epsilon. Now if we replace sigma with F over A from this equation, and epsilon with delta L over L from this equation, we can rewrite the equation, the Hooke's law, as this. And then if I take the A to the other side and combine EA over L like this, I can write F is equal to EA over L times delta L. Now here, F is the force, and delta L could be my new x, and as a result, the stiffness of the bar like this would be EA over L. So stiffness of the bar is equal to E, Young's modulus, times A, cross-section area, over L. So in finite element method, or FEM, every model can be discretized or meshed into several nodes and elements. Meshing or discretization of a solid model into a number of elements and nodes is very important in finite element method, and we will learn about this throughout this course. And elements and nodes are the essential parts of a finite element model to solve a problem. Again, we will cover these more throughout the class. A simple spring that we covered in this course, or in this example so far, can be modeled as one element and two nodes, like this. We denote the elements with a circle, and the element number is put inside the circle, and the nodes at the two ends of the element are just shown like that with two numbers. So we have node 1, node 2 for element 1. The nodes can have loads like forces, moments, and fluid flow if we're studying 1D fluid flow. And they can also have degrees of freedom such as displacement or temperatures. And elements have stiffness, and as we will study later, we can also have stress and strain defined for the elements. And we will learn about these later in the course, how we can get the stresses and strains for a typical element. So basically what the stiffness matrix does, it relates the vectors of nodal forces to the vector of nodal displacements. If you remember from this slide, the first slide, we have force and we have displacement, and this is the stiffness of the spring. Now we have multiple nodes, we can have multiple forces, and that would be something like this. And then we can have a stiffness matrix K and displacement vector d. So what this will do, the stiffness matrix will relate the nodal forces to nodal displacements.